Namaste, my name is Vijay Shenoy. I am at the Indian Institute of Science. I'm going to be offering this course on statistical mechanics of phases and phase transitions. So let's get started. So in the first lecture, we have an introduction. The introduction will contain two parts. In the first part, we will introduce the subject and give you a motivation. In particular, we'll address two things. What are the key questions that we'll be addressing in this course? And then we'll go on to explore what different subjects and topics can be explored using the ideas that are introduced in this course. Following this, we will review the necessary background and prerequisites. Essentially, there will be two sets of things we will be reviewing. First is thermodynamics, which all of us would have studied in the undergraduate programs. And we will then go on to explore a little bit of statistical mechanics, and then we will set the foundation for studying the more advanced topics. How should you use these lectures? So, lectures are intended to be participative. Key ideas will be indicated by a light bulb. So, this will give you sort of an idea of importance of the topic or the point that is made. And viewers are encouraged to think along, and I have included certain questions that will be posed to the viewer, and I encourage you to answer the questions before you proceed. You can pause the video, answer the question, and then proceed. So this will allow you to get a deeper understanding of the subject. Okay, so let's get started. So our first goal is to figure out why we should study this subject and what this subject is about. So the title has two things: phases and phase transitions. So it's a good idea to start with trying to understand what are phases. So if you look around, you will see many things, and most large things can be classified into the following classes. You can think of them as solid, liquid, or gas. And these three things we have studied as phases of matter in our high school courses. But then if you think a little deeper about this, you have to ask, what really is a phase? How can we make that concept clear and mathematically well defined? So let's explore. So let's take three things: a block of wood, a piece of stone or a block of stone, and let's take a gold bar. What is common in these? The common thing here is that all of the three are solids, although they are made of different things. So different things organize themselves into solids, and yet we call them the solid phase. So how can we characterize the solid phase? In other words, what do you mean by solidness of solids? So take a moment, pause the video, and think about how you would characterize the solidness of solids. So the answer to that question is very intuitive. If you think about it, every solid that you know will resist shape change. This is what we actually use solids, this is why we use solids to make buildings, to construct engines, and so on. So how can we characterize this? So imagine that I have something like a cube of a solid, and I try to change its shape by acting some shear stresses on it. So I change the shape of this cube by applying certain shear stresses. How do I characterize the change of shape? I characterize the change of shape by measuring the angle of deformation, that is how much the angle, this 90-degree angle has changed to something less than 90-degree, and let us say the change of angle can be characterized by an angle gamma. This is typically called as shear strain, and this measures the shape change of the solid. So, the question we ask is, how is the shear stress related to the shear strain? So, if you explore this, you will see, and I am sure all of you have studied this in your elementary courses, you will see that there is a relationship which relates the shear strain to the shear stress via a material parameter called as the shear modulus. The shear modulus mu is different for different materials. So, for example, for wood it is about 500 megapascals, for stone it is about 20 gigapascals, and for gold it is closer to 30 gigapascals. So, different materials have different solids have different shear moduli. So, you may think, okay, they are somewhat different, but let me show you that you can think of them in a universal way. So, now what I am going to do is, I am going to measure the shear stresses in units of the shear modulus. So, what I define is, I define something called tau tilde, which is tau by mu. So, this is now a dimensionless number which measures the shear stress in the units of the shear modulus. And now you see something very beautiful. This equation which we had written, gamma is tau by mu, becomes gamma is tau tilde, and note that this equation is same for all solids, in the sense that if I measure the shear stress in terms of the shear modulus, then solidness is characterized by the fact that shear strain is equal to the dimensionless shear stress that is acting on the solid. So, now we have found a sort of a universal way of describing all solids, and this equation that you see here tells you that all solids are sort of described by such a universal relationship, and this is what we will call as the solidness, or the property of being a solid phase. Okay, so I will just go through this again. The relationship gamma equal to tau now describes the universal property that describes the resistance to shape change experienced by all solids, and this describes the solidness. But now if you think about this, you will see that this gives a different kind of puzzle, a more conceptually interesting puzzle. So, now let us just look at what is wood made of. Wood is made of some dried up cells. You know, these cells can be several microns big and so on. If you look at stone or granite, you see that that's made of some silicon dioxide and aluminum oxide and all that, and it sort of has a interesting microstructure as I'm showing here. And if you take a crystal of gold, it's made of gold atoms, individual atoms sort of stacked up in something called the face-centered crystal. And you see, so the structure of these things and the constituents of these things, of these three examples that we have seen, they are all different. Yet, all the solids that form out of this, they are described by this universal relationship, which is that gamma is equal to tau tilde. So, we can pose this question, the interesting aspect of this question, in a different way. How does the solid forget what it was made of? So, it seems that the solidness has lost its identity of its constituents. All solids tend to lose the identity of its constituents when viewed in this way, that they all resist shape change in a certain universal way. So, the key moral of our discussion here is that different constituents, it can be cells, molecules or atoms, when there are many in number and start to interact with each other, they form things which have character distinct or unique to the phase that they form. And these phases have certain common universal properties, and this is our intuitive idea of what a phase means. Okay, let us proceed a little further. So, when many interacting degrees of freedom organize or many degrees of freedom interact with each other, they will organize themselves into phases. So you can stop the video and think about what is the characterizing property of the fluid phase. We have just discussed the characterizing property of the solid phase. So if you have found the answer to that question, you can ponder. We discussed what happens when atoms and molecules or cells interact. Can electrons interacting with each other form phases? This is something you can think about. Okay, we move on. Let's go back to atoms, and now we realize that the same atoms or molecules, they can form distinct phases. For example, we all very well know this, that if I take water molecules, when they are at very low temperature, say less than 0 degrees centigrade at atmospheric pressure, they will form a solid which we call ice. And if you melt ice, you will get liquid water, and if you take it about 100 degrees centigrade, it will boil into steam. And we know that these are the three phases of water. So the same constituents, depending on the conditions like temperature and pressure, can organize themselves into distinct phases. So how can we characterize all of this? So the way we characterize this is by using what are called phase diagrams. So when lots of atoms and molecules interact with each other, we get different phases. I am showing you here the phase diagram of carbon dioxide. What is plotted on the y-axis here is pressure, and what is plotted on the x-axis here is temperature. So you can see that at low pressure and temperature, somewhere here, you have a solid. And if you are at atmospheric pressure, you heat solid carbon dioxide, it will go into the gas phase. As you know, carbon dioxide sublimes, as we say from high school physics. And you have these three phases: the solid carbon dioxide, the liquid carbon dioxide, and the gaseous carbon dioxide. And there are solid and fluid phases, and these phases are separated by phase transitions. So for example, if I look at this particular point here, that is the sublimation point, or the point where solid carbon dioxide becomes gaseous carbon dioxide. This would be the melting transition, where solid carbon dioxide goes to the liquid phase of carbon dioxide. Now, I am sure all of you have studied this in high school physics, that the solid liquid transition is a first order transition. We will see more in detail what first order means in a few slides. But the most interesting point here probably is this point, which is called the critical point. The critical point is the end point of the first order transition line separating the liquid phase and the gaseous phase. Interestingly, you can take a liquid to a gas without encountering any phase transition. So what you would do, for example, is you would first keep the system at, let's say, this temperature, this pressure and 0 temperature, let's say, increase the temperature and then reduce the pressure and then reduce the temperature back. So you can see that I have gone from liquid phase of carbon dioxide to the gaseous phase of carbon dioxide without going through a phase transition. So in that sense, the gaseous phase and the liquid phase are not very distinct. So this is why we use the word fluid phase to describe them. And the most important and interesting point in this phase diagram probably is this critical point, which we will describe by something called as a continuous transition. So in some sense, the liquid changes to the gas here in a continuous fashion without undergoing like a sudden jump that you encounter in a first order transition. So I've already made this point that the liquid can be transformed to the gas without encountering any phase transition. Okay, so we saw carbon dioxide is like a small molecule. So we can ask what happens if I have larger molecules. So you can start with some very large liquid molecules and you can put them in a medium, and they will organize themselves depending on the conditions into different phases. So there are distinct kind of phases that you can get here. So these are called micellar phases, vesicular phases, layered phases, lamellar phases, and variety of phases you can get. So you see what is happening here. The constituents have changed, but the idea that you can get different phases, that idea still remains. And I have to emphasize this point that these phenomena are very important in biological systems and in fact for life itself. So phases and phase transition and all the physics that is behind this is actually the physics that governs life itself. Okay, so I started with atoms and small molecules and then moved to bigger molecules, and now I'm going the other way. I'm going to things that are smaller. I'm going to start with I'm going to have electrons, a large number of electrons that are going to interact with each other, and I'm going to ask if they can form distinct phases. So phases of electrons. So perhaps the most spectacular phase of electron is the superconducting phase. So all of us know that if I take a metal, the metal has a resistance that increases upon increase of temperature. And if you keep reducing the temperature, and this is a very famous experiment of Kamerlingh-Onnes, at about 4.2 Kelvin in mercury, the resistance suddenly plummets down to 0, and you essentially get a non-resistive system called as a superconductor. Now we know that the superconductor is a distinct phase of electrons. So there is electrons themselves can form different phases, and there can be phase transitions between them. So this is what is called as the normal phase above 4.2 Kelvin, where you have a regular metal, and when you go temperature below 4.2 Kelvin, you get the superconducting phase. I am showing you another example of vanadium molybdenum oxide, and here what you have is you have a phase transition and different phases that are gotten by changing the concentration of molybdenum. So you have an insulator here at low temperatures, say at when X is equal to 0.1. If you increase temperature, there is a phase transition to a metallic phase, and you can, by changing X, you can get various different kind of electronic phases. So the upshot of this slide is that electrons also can realize distinct phases depending upon the conditions, and there are various different kinds of phases: insulators, metals, superconductors. There are many more very recently discovered called topological insulators, etc., which I am not showing you here, but are very exciting and very active area of current research. Okay, I have discussed phases that can be formed by starting with electrons, but you can also start with even more exotic degrees of freedom like spins. So we are talking about the spins carried by electrons or individual ions or things like that. So these spins will interact, the spins are sitting in the system, and they will say, for example, the sides of a lattice, and they can interact with each other and they can form distinct phases. So these phases are typically characterized by some kind of magnetization. So what I am showing you here are the very classic examples of metallic ferromagnets. So you can take any metal like iron, cobalt or nickel, and as you cool them down, below some critical temperature, they develop a spontaneous magnetization. But you can work with totally insulating magnets. So I am showing you an example of europium oxide here. So you see above this roughly 70 Kelvin, there is no magnetization, and as you cool the system down below 70 Kelvin, you see that the magnetization pops up and it grows as you reduce the temperature, signaling the presence of a magnetized state. So the phase above Tc, or the critical temperature about 70 Kelvin, is what we call as a paramagnetic phase, and the phase below is a magnetized, below 70 Kelvin is a magnetized phase. So these two are distinct phases of the spin system. Now spin systems are extremely rich, as you can see in the slide, in the panel shown here, and this is a very interesting compound called cerium antimony. Depending on the temperature, it can form a variety of different ordered phases. So for example, you can form antiferromagnets. Antiferromagnets are magnetized systems where you have magnetic order in such a way that the spins are pointing one way in certain lattice sites and the opposite way in the other lattice sites. And you can get much richer kind of magnetic structure in depending on the material, etc. And I am showing you here a variety of phases realized, and all these sort of regions are distinct phases. They are labeled by these things here, and you can see that there are also phase transitions between them of various different types. So the upshot is that metals and insulators can show magnetized phases at low temperatures. Spins can order in different ways. They can be ferromagnets or antiferromagnets. And in complex magnetic materials like the ones that we have just discussed, there can be very rich phase diagrams with various different kinds of magnetic phases. Okay, so far we have seen phases and phase transitions particularly which occur at finite temperatures and pressure, or some doping, or some such parameter that we have. But all the transitions that we have seen, they occur at finite temperature. We will now visit a very interesting and extremely exciting area of physics called as quantum phase transitions, and these are in systems that are of great interest currently. So what I am showing you here is the phase diagram of what are called as high temperature superconductors. So this could be like lanthanum copper oxide or any one of these class of materials. So what you have here is you can dope the system by changing the concentration of electrons in the material, and what is shown here in the x-axis is the amount of doping you are doing in the system, and y-axis of course temperature. And you can see that there is a line here which is extrapolated from the experiment to 0 temperature. So if you move along this line, you are essentially working with the ground state of the quantum system, the lowest energy state of the quantum system. So let's look at small doping. You see that the system is denoted by AF, which means it's an antiferromagnet. So at some critical doping, you see that antiferromagnet changes to what is called as a D-wave superconductor. There is a lot of complicated other phases here with some charge density wave, etc., which I am not talking about. And then if you keep increasing the doping above certain other critical doping, you go to something called a Fermi liquid, which is not a superconducting state. So essentially, by changing this doping at 0 temperature, you are engendering a phase transition in an electron system from an antiferromagnet to a superconductor to a Fermi liquid. So these phase transitions are actually now controlled by the physics that's operative at 0 temperature, namely quantum mechanics. There are no thermal fluctuations at 0 temperature. That's what we mean by quantum mechanics. So everything is governed by quantum mechanics. And the class of phase transitions that take place at 0 temperature are called as quantum phase transitions. Okay. So let me summarize what we have learned from the experiments so far. When many degrees of freedom interact, they organize into phases. Distinct phases can be realized by the same degrees of freedom depending on the temperature, pressure, and other conditions. Phases are separated by phase transitions. Phase transitions can be first order or they can be continuous. So what do we mean by first order transitions? First order transitions are characterized by abrupt changes of properties. For example, the density of water changes discontinuously when freezing from liquid to solid. The change of density is discontinuous. Typically, first order transitions are accompanied by latent heat. That is, if you are trying to change the state of liquid water to solid ice, once you hit 0 degree, you have to remove a certain amount of heat to be able to further cool the system below 0 degrees. So you have to remove all the heat from the liquid to make it into the solid phase, and this is what we call as latent heat. Okay, now the latent heat is a very important quantity, and I have shown you in the 2 slides prior to this that there is a first order transition line separating the liquid and the solid. So what I would like to invite you to do is to take the PT phase diagram, the pressure temperature phase diagram, and relate the latent heat to the slope of the first order boundary separating the liquid and the solid. Okay, that's how much I will have to say about first order phase transitions. But I want to emphasize now that continuous transitions are far more interesting and absolutely fascinating, which I will demonstrate in the next few slides. Okay, so what are continuous phase transitions? So continuous phase transitions are characterized by a continuous change from one phase to the other. For example, we saw this magnetization. The magnetization was 0 above Tc, at Tc it's also 0, and then it starts to gradually increase. You should contrast this with like the density change that I mentioned about the first order transition between the liquid and the solid. Here the magnetization is 0 at the transition point and then starts to grow gradually as you reduce temperature. This is in this sense it's a continuous transition. This transition is characterized by a divergence of the magnetic specific heat. So if you plot a specific heat around the transition point here, you will see that the specific heat seems to diverge. Similarly, if you look at the magnetic susceptibility, you will find that the magnetic susceptibility is also divergent. So there are divergence of properties such as specific heat and susceptibility. So how do we characterize this? So the way to think about this is to define a dimensionless parameter called as little t, which is the temperature minus the critical temperature divided by the critical temperature. Note that this is a dimensionless parameter as opposed to the temperature or the critical temperature, which has certain units. So the phenomena that we have seen here, namely that you have these divergences, are characterized by certain functional dependence of these quantities, namely the magnetization or the specific heat or the susceptibility, on this dimensionless reduced temperature, little t. So for example, if I look at the specific heat goes on the plus side as a constant C alpha. C alpha is a notation to say that that's the constant associated with the specific heat, with mod T exponentiated with an exponent minus alpha. This is the convention. So for example, alpha in this case would be some positive number showing that there is a divergence. Similarly, there is a constant associated with susceptibility, and there is an exponent called as gamma, and these C's, like I said, are constant, and plus or minus subscripts that indicate whether the constant is associated with T greater than 0, namely on the paramagnetic side, or with T less than 0, which is in the magnetized side. Okay, so that is, if you are on this side of Tc, say for example in this picture T something like 4 Kelvin or something, then it will be, the susceptibility is characterized by C plus gamma T to the minus little gamma. Okay, so these quantities alpha, beta, gamma are called as critical exponents, and C plus alpha, beta, gamma and C alpha, beta, gamma for each of alpha, beta, gamma are again dimensionless quantities. So these ratios will be called as dimensionless, and these are called as amplitude ratios. So these things, these quantities that come that exponentiate T are called critical exponents, and the ratios of these quantities on the paramagnetic by the ferromagnet or the magnetized side are called amplitude ratios. Okay, so continuous phase transitions have this idea of universality, and that's what makes them very interesting. Okay, so continuous phase transitions can be understood by looking at dimensionless quantities associated with different materials. So what I am plotting here is temperature divided by critical temperature and density divided by critical density, and this is for variety of different materials. So you see that when you plot it in this way, they all fall on the same curve. So now here is something remarkable that comes out of this. If you plot the critical exponents, or if you calculate the critical exponents for all these different materials from this data, you will find that the critical exponents of the liquid gas critical point is the same for all these materials. So again, just like we had seen from the property of phases, we now see that the critical point separating the liquid gas forgets what the material is, in the sense that it picks up some universal properties. So this is actually characterized in the table given here. We can see very different systems have the same critical exponents irrespective of what microscopic constituents were producing the phase transition. There are different types of criticality here. So you see in these three columns, there are three different systems. They have the same criticality. Then there is this helium system which has one kind of criticality, and then there is this iron and nickel which have another kind of criticality. So what one sees is that the critical exponents of variety of systems turn out to be the same, but different kinds of continuous phase transitions have different critical exponents. Now here is something absolutely remarkable. If the magnet were what is called as an Ising magnet, we will see more details later what an Ising magnet means. The critical exponents of the Ising magnetic transition would be same as that of the liquid gas. So it even forgets that one was made of spins and the other was made of atoms and molecules. And like I said, these critical phenomena, they organize themselves into universality classes. What are universality classes? So like I said, these three systems, they will form, that's sort of indicated by these numbers, they will form one class of critical phenomena with the same critical exponents. This will form another class of critical phenomena with the same critical exponents. They may be different from what you find in this class, and similarly this is the third class of critical universality class. So this is why we call as universality class of critical phenomena. Okay. Now here comes another extremely interesting and intriguing result. So I had introduced these parameters called as alpha, beta, gamma, which we had called as critical exponents. Now these critical exponents will satisfy something called as scaling laws, irrespective of which universality class they are in. So for example, alpha plus 2 beta plus gamma will be equal to 2 in all of these classes. Okay. So this is the phenomena that we want to understand. So what is the goal of this course? The goal of this course is to understand how to describe phases. We will learn a variety of analytical and numerical methods to study phases. We will uncover the origin of universality and learn an extremely important idea in physics called as the renormalization group. So what would you have to have known to do this course usefully and learn something? So you should have learned some advanced undergraduate level, like third year BSc or first year MSc level of classical and quantum mechanics. You should have been exposed to some elementary thermodynamics. You must have some idea of what free energy is, what Helmholtz free energy is, Gibbs free energies, and so on. And you must have had an introduction to statistical mechanics. For example, you should know the different kinds of ensembles, and you should be able to do some elementary computations with those. But you have to always wonder, why worry about all this? If you look at all the experiments that I showed you, they were from about 20-30 years back. So why worry about all this? So my first point is that phases and phase transitions are there in all of physics. So if you look at high energy physics of quarks and gluons, you see that there is a fantastic phase diagram for this. And these are the kind of experiments that are being done in these heavy ion collision experiments and so on. They are being probed in these heavy ion collision experiments. In fact, if you take a neutron star and study its structure, you see that different layers of the neutron stars have different phases of variety of different types of matter. So you can see phases and phase transitions go from the smallest scales to objects that are very large scales, astrophysical scales. More importantly, using this picture that I got from the internet, you can see that all the knowledge that we have obtained is by probing nature on variety of scales. At least we have probed from this quark scale all the way to the scale of galaxy and universe, etc. I don't know about, we haven't probed to this small scale yet. And you see that there is an interesting puzzle. The puzzle is, how is it that I am able to build a satellite and send it out to space without knowing or having to know the fact that nature is made of leptons and quarks? I don't need to know that. So somehow the information from this scale, it comes in a packaged form on the scale of, on the human scale. And somehow there is this forgetting details kind of thing as you go more, as you go to larger and larger length scales. So actually the study of phases and phase transitions gives us an answer to why we are able to start from one scale and study what comes at a larger scale in a very nice way. In fact, what we have learned here is a framework to build physical theories, and this goes by the name of Landau-Ginzburg-Wilson paradigm. So an important aspect that we'll cover in this course is to discover how we get Landau-Ginzburg-Wilson paradigm. Okay. So I have to also flash a couple of slides to show you that they're absolutely important for the most interesting and important things that are going on today, that is quantum technology. So you can show that there is a deep connection between quantum error correction and phase transitions. And I'm showing you here some experiments from Google which produce what are called measurement induced quantum phase transitions. So what happens is, you start from some entangled state and you evolve the entangled state in time, and every now and then you measure it. And there is a rate of measurement, and by changing the rate of measurement, you can change the nature of entanglement, and there is a transition from one kind of entanglement to another kind of entanglement, and magically this is described by phase transitions, by the theory of phase transitions that we in fact are going to cover in this course. And even machine learning and artificial intelligence, which is also very hot these days, that has also connections to phases and phase transitions. So for example, I am showing you here some network that can classify pictures into dogs and cats. So you see, this is deeply related to universality. So even if you take a picture of dog and sort of deform it, if you run it through this network, it will classify it correctly because it sort of looks at some very essential features, pretty much like how a system near a critical point forgets what it was made of and picks out the essence of the liquid gas phase transition and gets the same critical exponents. Similarly, a network finds out what is the dogness or catness. So this is, dogness is like some property of the dog, right, which the network finds. So there is some connection like this. So you can see that, we could use some physics ideas to understand how a network learns and what it learns actually. Okay, so let me summarize this lecture now. So this lecture is meant to be an advertisement for this course, and what I hope to have conveyed is in phases and phase transitions are ubiquitous in all of physics, and the ideas arising from this have very wide applicability, and I hope you will join me in continuing with this course. Thank you.